All right, quantum mechanics. Quantum mechanics really started off about 120-ish years ago when people started realizing that if you look really closely at subatomic particles, or even atomic particles, molecules, atoms, protons, neutrons, electrons, and their behavior, it acts a little like classical mechanics, like the behavior of just individual particles bumping into each other, but not exactly. There are differences that can't really be explained by classical Newtonian physics. So quantum mechanics is largely, or at least largely grew out of an attempt to explain why very small particles don't behave in the way we think they should at first. And it's mostly classical mechanics plus a few new ideas about how very small things behave, plus a bunch of math. The big ideas largely consist of, first of all, that particles and waves aren't really different things. Classically, we tend to think of particles and waves as very different. Like a particle would be, for instance, let's say you have just a rock that has been thrown, and so it's moving with some velocity. Versus a wave would be something like a rope, or let's say a sound wave. You've got some particles that are bunched up close together, and then particles spread further apart, and then particles bunched up close together, then particles spread further apart. And so you get oscillations of how close or how far the particles are, usually graphed as a wave, or as a comparison of high pressure, low pressure, high pressure, low pressure. As a graph of, for instance, position versus pressure. So classically, we tend to think of these as very different things. For example, what are some properties that a particle has? If you just got like a rock and you throw it, what are some things about that rock that could be measured? It's got momentum, right? Because in terms of physical practicality, you could measure the mass of the rock, you could measure how fast it's moving, multiply those together, you got momentum. So a particle has momentum. In fact, you could think of the momentum as sort of the defining aspect of the particle. The wave, on the other hand, even though it's also moving, the particle has momentum and the wave, or sorry, the particle has velocity and the wave also has velocity. The wave is a traveling phenomenon. So that's kind of what they have in common. But we wouldn't typically say that a wave has momentum. You wouldn't like look at a sound wave and say this sound wave has a momentum of 5 kilogram meters per second. But what are some aspects of a wave that you can measure? For instance, if you've got an X versus pressure graph, what could you measure about that? Yeah, you could measure the wavelength. And of course, plenty of other properties as well, like the period or frequency and the amplitude, the phase shift. But wavelength is really the key attribute we're going to be looking at here. Classically, a particle in motion has momentum, but does not have wavelength. A wave in motion has wavelength, but does not have momentum. So you can think of these as sort of the defining attributes of these two different types of phenomena in motion. They both involve motion and speed, but momentum and wavelength are sort of the distinguishing attributes. That's the classical approach. The quantum mechanics approach says that particles and waves aren't really different things. The things we tend to think of as particles, yes, they have momentum, but they also have wavelength. And things we think of as waves have wavelength and also have momentum. So any moving phenomenon has wavelength and momentum, and they're related by this idea of the de Broglie equation. Specifically saying that the wavelength of a moving thing times the momentum of that moving thing multiply out to this constant called Planck's constant. I don't remember its exact value, but it's extremely small, like something times 10 to the negative 34. So the particle, like if you throw a rock, it has a momentum you could directly calculate. You can measure its mass, measure its velocity, so you can find its momentum. How would you find its effective wavelength? if you know the momentum, how would you find wavelength here?
Would you divide momentum on both sides?
Yeah, we could divide both sides by momentum. So the rock that is being thrown has a classical momentum. Classically, we would just say it has momentum. You multiply its mass times its velocity. But in the quantum approach, it also has what we call a de Broglie wavelength, or an effective wavelength. So that would be effective wavelength equals Planck's constant divided by the momentum. But since Planck's constant is ridiculously small, like something times 10 to the negative 34th, I think, you divide by the momentum. Let's say the momentum is, I don't know, 50 kilogram meters per second. This extremely small number divided by 50 or whatever it is going to result in a ludicrously small wavelength. In fact, probably specifically much smaller than the rock itself, but also I would expect probably smaller than an atom. So technically this rock does have a wavelength according to the de Broglie equation, but it's such a ridiculously small wavelength that it doesn't even matter. So classically, this is why we think of particles and waves as different things. Our projectiles, I guess we should really call that a projectile, not a particle. Projectile motion this projectile, or I guess you could call it a particle, either way works, has a momentum that is significant. It technically has a wavelength, but that wavelength is so small that it may as well be zero. So pragmatically, there's no real reason to treat this thrown rock as a wave. Likewise, the wave has a classical wavelength, but according to quantum mechanics, it also has a momentum. You could solve for momentum in the same way. The effective momentum, the de Broglie momentum, you'd get by dividing both sides by wavelength. But once again, the Planck's constant is ludicrously small, something times 10 to the negative 30 something. The wavelength, let's say this is a wavelength of maybe 2 meters or something. You take a ridiculously small number, divide by 2 meters, it's going to get even more ridiculously small. So this wave technically does have a de Broglie momentum, but it's so small that there's no reason to even consider it worth mentioning. So classically, the sort of particles you see in everyday life, like a thrown rock or a car moving along a road or something, is just a particle. There's no reason to treat it as a wave because its wavelength, its effective wavelength is so small. Likewise, the sort of waves we see in everyday life, like ripples in a pond or sound traveling through air, technically has a momentum, but its momentum is small. There's no reason to worry about it. So in everyday life, we can typically treat waves and particles as two completely different phenomena. But where it becomes kind of a more fuzzy distinction and not really different things sort of situation is when both the wavelength and momentum are small. If you're dealing with very small objects, like an electron, for instance, its momentum is small enough that its wavelength is not negligible. We have to consider the electron as having momentum and wavelength, so it acts like a particle and a wave at the same time. Same thing with light. Light has a very small wavelength. I mean, typically we do think of light as a wave, and it is. It has a wavelength. But its wavelength is so small, like maybe just a few nanometers or a few hundred nanometers, that its momentum cannot be ignored, especially when you're comparing it to momentum of, let's say, an individual atom that it's interacting with. So on the very small level, we have to consider most moving phenomena as both particles and waves at the same time. That's one of the biggest ideas of quantum mechanics, this shift in perspective from these are waves, these are particles, and never they shall meet, to waves and particles are just different ways of looking at the same thing. Any questions on that so far? So let's take a look at how we would actually apply this to the idea of a particle in a box. If we've got a small particle, let's say an individual electron, that's in a small box, and for simplicity, we're going to assume it's a one-dimensional box, like a long, narrow pipe, for instance. Let's say you've got this long, narrow pipe, So we're treating this as a one-dimensional box, and you've got an electron in this box. Classically, we would treat the electron as a particle. It would just be like a tiny ball bouncing back and forth in the pipe. But in the quantum approach, we have to treat that electron as having a wavelength also. We have to treat the electron as acting like a wave. That means it's a wave that's confined to a finite space. And what happens if we've got a wave in a finite space? What kind of behavior do we get there? Exactly, it becomes a standing wave. So the electron, treated as a wave, in this confined space, becomes a standing wave, which means only certain wavelengths will work. And if you take a look at the graphs of that standing wave, the wave we're talking about here, I mean, anytime you're talking about a wave or vibrations or anything like that, the big question should be what's vibrating? Like ripples in a pond, the height of the water is vibrating. Sound waves, you could say the pressure of the sound is vibrating, or the pressure of the air is vibrating. But for the particle, the treating the electron as a particle and a wave, what's vibrating is a little more difficult to pin down. There's this, mathematically, we just call it the wave function of the particle. But you can think of it as essentially representing probability. What's oscillating is the probability of there being a particle there. That a high oscillation, an antinode, means there's a high probability for there to be an electron there. Low oscillations means there's a low probability for finding an electron there. And a node where there's zero amplitude means there's impossible to find an electron there. And if the particle's in the box, what would you expect to be the probability of the particle being outside the box? Right, we should expect zero probability that the electron is outside the box, which means the endpoints should be nodes or antinodes in this case. Yeah, they should be nodes. We should expect zero probability of the electron being outside the box, which means the endpoints need to be nodes. So we're going to have nodes at the ends. And we could look at this as the same type of standing wave as the standing waves we get on a string that's fixed on both ends, because that also has nodes on the ends. So the simplest case would be n equals 1, looking like this. This standing wave just means there's a high probability of the electron being found near the middle, low probability of it being found near the ends, and zero probability of it being at the ends. Or for the n equals 2 case, we would add in an extra node and then have antinodes in between those. So this would mean high probability of the electron being found in this region or in this region. But in this case, you're never going to find the electron exactly in the middle. And it's very unlikely to be even near the middle. Or the n equals 3 case, we'd add in more nodes. And so you'd be very likely to find an electron at the antinodes and very unlikely to be finding the electron near the nodes. Now, this doesn't really play much of a role if you're just measuring the electron once. But let's say you have an experiment where you measure where the electron is. Like you take a sample and figure out where is the electron. And let's say you repeat this experiment many times. What you would find is, if you, let's say you put a dot every time you find an electron, you're going to get clustering. If you repeat this experiment over and over again, you're going to very frequently find an electron in one of those spaces represented by the nodes, or sorry, the antinodes. And you're going to very rarely find the electron in the nodes or near the nodes. In theory, you should never find it at the node. You would occasionally find it near the nodes, but not very often. And you would most frequently observe the particle at or near the antinodes. Because this graph essentially represents what's the probability of finding an electron at each of those locations. Any questions on the meaning of that wave so far? And this also means, since the electron is acting like a standing wave, we can apply everything we already know about standing waves in strings. For example, the wavelength. What formula do we have for a wavelength of a standing wave in a string like this? If it has to be nodes on the ends. Yeah, 2L over N. where n is just some whole number representing which state we're in. The n equals 1 state, the fundamental vibration, n equals 2, n equals 3, second harmonic, third harmonic, and so on. So those are the possible wavelengths of the electron if we're treating it as a wave. But if it has a wavelength, what else does it have, according to the de Broglie equation? Right, if it has a wavelength, then it also has a momentum. So much in the same way that for the sound waves from a stringed instrument, we were using the wavelengths to find possible frequencies. Here, we're going to use the de Broglie equation to use the wavelengths to find possible momenta. So we can do that just by replacing lambda with 2L over n. Isolate P by multiplying both sides by the reciprocal, n over 2L. So that means these are the possible momentum. Momentum of the nth state, or rather momentum of the electron when it's in the nth state, must be h over 2L times n. So there's only certain possible values of momentum. And this is very unusual. I mean, not so much unusual, it happens all the time. This is what happens this is how electrons behave. But this seems unusual compared to what we see in everyday size objects. If you're just like throwing a ball at a wall and letting it bounce back, you could throw it at any speed you want. There's essentially infinite variability in how much momentum you give the ball. But this electron, in order to form a standing wave, the wavelength has to be specific values, 2L over 1, 2L over 2, 2L over 3. The in-between values don't work because they don't form standing waves. But since wavelength determines momentum, there's also only certain values of momentum that will work. H over 2L, H over 2L times 2, H over 2L times 3, H over 2L times 4. Only these whole number multiples of H over 2L will work. In-between values of momentum do not happen because they don't form standing waves. Any questions on that so far? And the usual terminology we use for that is we would say that this quantity, this momentum, is quantized. Quantized, or we also use the term discrete. That's discrete ETE, meaning not continuous, as opposed to discrete EET, meaning secret. But discrete in this context just means it's not continuous. There are certain levels that work and the in-between values do not work. So you can't just have any momentum. You can only have momentums that are whole number multiples of H over 2L. Any questions on that so far? And I think this is really where the word quantum in quantum mechanics comes from in the first place, that we call it quantum mechanics because these values only occur at certain quantum values. They don't occur in between, they only occur at these quantized quantities. Also, if it has momentum, what type of energy is usually associated with momentum? Yeah, kinetic energy. If we have a formula for momentum, we can turn that into a formula for kinetic energy. And how do we do that? How would you convert momentum into kinetic energy? What formulas would link those together? Yeah, if we go to the classical approach, classically we would say kinetic energy equals 1/2 of mv squared. And what's our classic formula for momentum? Yeah, mv. So these are definitely related to each other. They both involve mass and velocity. And one very useful way of linking them together is if we square the momentum formula, because we want a v squared. If we square momentum, we get m squared v squared. Is that the formula we want for kinetic energy? It gives us the v squared we want, right? But it also gives us too much m. It makes it m squared instead of just m. So what do we need to do to m squared v squared to make it look like mv squared over 2? what other operations do we need to do here to make this look like mv squared over 2? Yeah, we could divide both sides by m, because squaring both sides gives us the right exponent on v. We want v squared, and we now have that. But we also need to divide both sides by m, so we just get m instead of m squared. We would also like to have it divided by 2. So let's instead divide both sides by 2m. That way, one of the m's cancel out. And what's left, mv squared over 2, is kinetic energy. So this gives us a very useful alternative formula for kinetic energy. Classically, we tend to think of kinetic energy as mv squared over 2, which it is. But you could also write kinetic energy as momentum squared over 2m. And this ends up being so much more useful in quantum mechanics, because we have some formula for momentum already, that we generally treat momentum squared over 2m as the definition of kinetic energy in quantum mechanics. It's not really a different definition, because it's still the same as mv squared over 2 and mv. It's just a different way of combining those formulas. But in quantum mechanics, we typically treat this as the foundational baseline meaning of what kinetic energy is. So the quantum formula, in quantum mechanics, we usually use kinetic energy is momentum squared over 2m. Not truly a different formula, just a different way of writing it. And the useful thing is here, you can calculate kinetic energy directly from momentum, which we have, and mass, which is just going to be the mass of one electron, without having to worry about how fast the electron's actually moving. Any questions on that so far? So let's try calculating that. We have a formula for momentum of the electron. We can combine that with the kinetic energy formula and figure out the kinetic energy. So all we need to do is take the momentum formula, square it, and divide by 2m. Kinetic energy is momentum squared divided by 2m. And if you square h and 2 and l, this whole thing is getting squared, so we can just write that as h squared times m squared. 2 squared would be 4, and then l squared. And we also have a 2m in the denominator as well, so we can just combine those denominators. And we get kinetic energy equals h squared n squared over 4 times 2 would be m L squared. So this now gives us a formula for the kinetic energy when it's in the nth state. And this is another big difference between the classical result and the quantum result. In classical mechanics, a moving particle can have any kinetic energy you want. But the quantum result here is that the kinetic energy can only work if n is a whole number. So you could have h squared over 8ml squared times 1, because that's 1 squared, or h squared over 8ml squared times 4, because that's 2 squared, or h squared over 8ml squared times 9, because that's 3 squared, or times 16, or times 25. This only works if n is a whole number. So you only get perfect square multiples of h squared over 8ml squared. So there's only specific values of kinetic energy that work. The in-between values do not happen because they don't form standing waves. So energy itself is quantized. This is one of the biggest ideas of quantum mechanics, that because we're treating the particle as a wave, and because it acts as a standing wave and only certain wavelengths work, that also means that only certain energies work. So these energies work as long as n is a whole number. The in-between values don't happen because they don't form standing waves. So this is what we mean when we say energy is quantized, or energy is discrete, as opposed to continuous. Any questions on that so far? Then let's try mapping out these energies as some examples. So still sticking with this one-dimensional box idea. And this is just one example of a quantum energy system. There's other energy systems as well. As somebody mentioned earlier, there's the oscillator, a quantum oscillator, which basically acts like particles on a spring. That also has only specific values of energy available, but it uses a different formula, not this one. And also the hydrogen-like atom. If you've got an atom with only one electron and then it acts enough like hydrogen, then there's a different formula representing the different possible energies that that atom can have as the interaction between the electron and the nucleus. It's still because it's acting like a standing wave. It just uses a different formula because it's not this simplified model of a one-dimensional box. But a lot of the behavior is very similar. It just uses a different formula. But let's try extending this. We know the kinetic energy in the nth state is h squared over 8ml squared times n squared. And I'm writing the n squared separately because everything else is constants. We've got Planck's constant, which is universal and doesn't change. We've got the mass of the particle, which is some value that doesn't change as time passes. We've got the length of the box, which is also not going to change as time passes. So the only thing that's different from one energy level to the other is the value of n. So let's try this. Let's try figuring out some actual values here. If you plug in, let's say 1, what would you get if you plug in 1 for n? Yeah, 1 squared is 1, so we just get this part, h squared over 8ml squared. And that's going to be the lowest energy the particle can have because any other n values are going to lead to larger results. So kinetic energy 2, you plug in 2 for n, and what does it become? Yeah, we get it times 4. So it's going to be the exact same fraction times 4. Instead of writing that out every time, I'm just going to write that as Ke1 times 4. And likewise for Ke3, the kinetic energy in the n equals 3 state. You plug in 3 for n, what do you get? Yeah, that'll just be 9 times as much. The base kinetic energy, and we usually call this the ground state. The lowest possible energy it can have is the ground state. And sometimes that's n equals 1, sometimes it's n equals 0, depending on which situation we're talking about and how the formula is set up. In this particle in a box situation, we've set up the variables so that the ground state is n equals 1. And then anything higher than the ground state would be called an excited state. So this is the first excited state above the ground state. This is the next excited state above the ground state, and so on. And then Ke4, an even more excited state, you plug in 4, we're going to get 16 times the ground state. So we just get these perfect square multiples of the base energy, the lowest possible energy. And note that this is very similar to what we were doing with the standing waves last time, the standing waves on a string. Then much in the same way that the standing waves you can get from a string only occur in specific whole number multiples of the fundamental frequency. And so you get notes that sound good together, the idea of chords. Here we're only getting energies that are not whole number multiples, but specifically perfect square multiples of the fundamental frequency or fundamental energy. So in a lot of ways, the quantum mechanics stuff is very similar to music theory. Not because it is actually music, but because it results in very similar ideas of some lowest possible value and then only specific multiples of that value work. So there's a lot in common. I mean, this is the reason why they're taught side by side. They're both involving standing waves and discrete values of some variable. So we get a whole bunch of values, and presumably Ke1 is going to be just some number, some very tiny amount of energy. Because that's going to be Planck's constant squared, which makes it even more tiny. And then mass of the electron is very, very small. Length is presumably like the size of an atom or something like that. So you've got a very small numerator divided by a very small denominator. Difficult to figure out exactly what that's going to be, but if you have numbers, you could plug those in. But the result I would expect to be pretty small because we're talking about energy of an individual electron here. Any other questions on these formulas so far? So let's try mapping this out, because just looking at all these formulas, it's very difficult to see what's going on. But if you make a map, a chart showing how these are related to each other, it's much easier to see what's happening. And what we usually do here is we typically draw a vertical line, which can basically be thought of as an energy axis. So this axis represents energy. We're essentially making a graph, but it's instead of a two-dimensional graph with an axis and another axis, we're essentially just making a one-dimensional graph here, a chart of energy. And let me put a 0 there. And let me mark some values here. Let's say each one of these tick marks represents KE1. So this is 1 KE1, and then the next tick mark would be 2 KE1, 3, 4, 5 KE1, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and so on. So each one of these tick marks represents this much energy. What we can do is we can mark the allowed energy states, the energy states that actually work here, as bars on this chart. So 1 KE1 works. This is one possible energy level. And then the next energy level that works is 4 times that much. So here's 4 KE1. N equals 2 leads to E2 being 4 times E1. And then the next one, we plug in N equals 3, we get 9 KE1. So let's go up to 9 on this graph. N equals 3, and the energy in the third state is 9 times energy 1. And then next one, 16. So we go all the way up to 16 times KE1. So each of these bars represents an energy that is possible for this electron to have. And then the next one would be 25, but that's off the chart, so I won't bother drawing that in. But each of these red bars represents a possible state for the particle, a possible energy that the electron can have. Any questions on that chart so far? And what do you notice about the spacing here? The spacing between state 1 and state 2, or state 2 and state 3, or state 3 and state 4, or state 4 and state 5 off the chart. Yeah, this spacing is getting larger. So from the ground state to the first excited state, that's not all that big of a gap. From the second state to the third state, that's a bigger gap. From 3 to 4, that's an even bigger gap. Because we're squaring the n value. In this formula, there it is. We're squaring the n value, and as n gets larger, the gap between n squared and n plus 1 squared gets larger and larger and larger. For example, if you look at a parabola, the parabola gets steeper and steeper the further out you go. So we're getting larger and larger gaps as we go up. And that's only true for this type of particle situation in specific. If you're looking at a different situation, you get different spacing. For instance, the hydrogen-like atom model. If you take a look at the formula for the hydrogen-like atom, which is negative 13.6 z squared over n squared, where z is the atomic number. Like for instance, for oxygen, it would be 8. And then n is any whole number. If you try drawing out a graph like this for that formula instead, you start with a very large gap from ground state up to the first excited state, and then a smaller gap, and then a smaller gap, and a smaller gap. So the gaps get smaller as you go up, if you're talking about that formula. Or if you take a look at the quantum oscillator, quantum harmonic oscillator, the formula for that ends up just being a direct proportionality. So instead of having gaps that get bigger and bigger or gaps that get smaller and smaller, the gaps in the quantum harmonic oscillator are equally spaced. So it takes a certain amount of energy to go from ground state to the first excited state. To go from first excited state to the next excited state, it's the same amount of energy. And then from the second to third, it's the same amount of energy. So for the quantum harmonic oscillator, all those gaps are evenly spaced. And that leads to very different sort of behavior. Because once you've mapped out the possible energy levels, and I would generally recommend starting with that, whatever system you're talking about, if you have some formula that allows you to calculate the energy levels, try just plugging in various small whole numbers for n, and try drawing out a diagram like this. Map out the possible energy levels so you can see how they're spaced out and whether that spacing is changing. And once you've got those energy levels, let's investigate the behavior of that system. You've got this particle in a box, and let's say it is currently in its lowest possible energy state. So right now the particle is at its lowest energy. We might say it is a cold system. Cold in the sense that it doesn't have much energy at all. Because you could sort of think of this as being like thermal energy. The individual atoms are very low energy, so that's essentially the thermal energy of the whole system. And let's say you want to raise this to a higher energy level. You're going to have to add energy to it. And how do you add energy to a quantum system? If you've got like an atom and you want that atom to gain energy, how do you provide that energy? Yeah, you use a photon, you shine light on it. And in some ways, this is very similar to the conservation of energy stuff we were looking at way back in 7A. Classical conservation of energy, delta energy of the system is work plus heat. The change in energy of the whole system is equal to the process or processes that cause that change. The quantum mechanics version of that is delta energy of the quantum system in this case, the electron in a one-dimensional box, or we might be talking about a quantum harmonic oscillator, a pair of molecules vibrating, or we might be talking about a hydrogen-like atom with one electron. But no matter what the system is, the change in energy of the whole system equals the process that's happening to make that change happen. But the process that's happening is a photon traveling. If you have this atom and you want it to gain energy, you do so by shooting a photon at it. That photon, that discrete packet of light, has some energy that it's carrying. When the photon hits the atom absorbs the photon and gains the energy that the photon was carrying. So a quantum system can gain energy by absorbing a photon. And the change in energy of the system equals the energy that the photon had. Alternatively, if you have a system that's already at high energy, how would that system be able to lose energy? Like if you drop from n equals 4 down to n equals 2, you're losing a bunch of energy. Where does that energy go? How does the energy leave the system? Yeah, it's emitting light. This atom or this box of the particle or whatever, in order to lose energy, it shoots out a photon, and that photon carries the energy that the atom has lost. And this is why, for instance, if you've got, let's say you've got a very hot metal, you've got iron that's been heated up to ludicrously high temperatures, that iron is going to glow. It's going to glow with certain colors. Like let's say you heat it up so it just barely starts glowing. It's going to glow sort of red-orange. The reason for that is all those very hot particles, they're all at high energy. And since they have so much energy and their surroundings don't have much energy, the iron atoms are going to be losing energy. They drop down to a lower energy state. As they drop down to a lower energy state, that energy leaves as photons. And for iron and some other substances, the energy lost corresponds to visible light. So the light that's leaving is very specific colors, based on how much energy was being lost. And the reason for that is the change in energy as it loses that energy going from one level to another level lower is the energy that the photon carries. Although we should probably put this in absolute value because the system might be gaining or losing energy. Delta energy might be positive or negative, but energy of a photon is always considered to be a positive value. So I would think of energy of the photon as absolute value of the change in energy. For example, let's say we want to take the electron from n=1 state up to the n=, let's say the n=2 state. So we've got an initial state and a final state. What's the change in energy there? How much is energy changing? Yeah, we're going from 1 KE1 to 4 KE1. So delta energy is 3 times KE1, 3 times h²/8mL². So that's how much energy that the system has to gain in order to go from here to here. It can't gain less than that because it cannot exist between these values. Between these values does not work because it wouldn't result in a standing wave. It could gain more than that if it gained enough to go exactly up to here. But so it could gain +3, or it could gain +8, or it could gain +15. But it could not, for instance, gain +7 because that wouldn't end at one of the permitted states. That wouldn't form a standing wave, so it's never going to happen. But let's say it absorbs exactly enough energy to go to the n=2 state. That means that it has to be absorbing a photon that has exactly this much energy. The only way the photon can be absorbed at all is if the photon happens to be carrying exactly the right amount of energy to bump the atom up or the system up to the next level, or the one above that, or the one above that. You can skip levels as long as you start and end on permitted levels. So these would all be allowed transitions, but anything in between doesn't work. And this leads to the other big idea of quantum mechanics, that the energy of that one photon depends entirely on specifically the frequency of the light. That the energy of one photon in particular is proportional to the frequency of the light. Light with high frequency has lots of energy per photon. Light with low frequency has less energy per photon. And that doesn't really correspond to the brightness of the light. The brightness of the light has more to do with how many photons the light bulb or whatever is emitting per second. But the frequency determines how the energy is split up. That each photon is going to have an amount of energy proportional to the frequency. And specifically, the constant in proportionality ends up being Planck's constant again. So the energy of one photon, which we know because it's the energy that the atom is gaining, the energy of one photon is Planck's constant times the frequency, which means if you know the energy of one photon, you can solve for the frequency. And that tells you the frequency and therefore color or type of light that's going to work here. Light with that frequency can get absorbed, causing the system to jump from 1 to 2. But light with a slightly different frequency won't get absorbed. It won't work because it does not allow the atom or system or whatever to end on an allowed energy state. So this is why certain types of chemicals or elements or whatever can only absorb certain colors of light. Light that's the right colors is going to get absorbed because it gains exactly enough energy to result in the system being in a permitted energy state. The in-between colors don't work. They don't get absorbed because they do not end in an allowed state. So those photons, instead of getting absorbed, they just pass right through without interacting with the atoms at all. So this is ultimately why certain chemicals are absorbing some colors of light, but translucent to other colors of light. And that would be called the absorption spectrum. The spectrum, in the sense of which colors in the rainbow or whatever, can be absorbed by that chemical. Whereas if you're talking about dropping to a lower energy level and emitting certain frequencies or certain wavelengths of light, that would be the emission spectrum. The spectrum of which colors of light can be emitted by that substance as it cools off to a lower energy state. And you can calculate those by looking at the differences. How much energy does it take to go from one state to another? And then using this fact to convert the energy change into a frequency. But note that the energy we're talking about here is not the energy of the system, it's the energy of one photon, which matches the change in energy of the system. Any questions on that so far? Also, one other way to write this that's sometimes more convenient. Frequency is the same as speed over wavelength. So we could also write this as Planck's constant times speed, specifically speed of light, divided by wavelength. Sometimes this is more convenient because wavelength of light is often more commonly used to describe the color than the frequency is. So you could use either one of these depending on, do you want the frequency of the light or do you want the wavelength of the light? Also, H times C shows up together frequently enough that it's usually just treated as its own constant, which I think is 1,240 electron volt nanometers. Electron volts is just a unit of energy that's often used here because it's a very small amount of energy. Any other questions on that? The relationship with frequency, yeah, the frequency of the light determines how much energy each photon has. So light that has high frequency, which means low wavelength, is going to have lots of energy per photon. Light that has low frequency and therefore a longer wavelength is going to have only a little bit of energy per photon. And the important thing about the photon is, in order to get absorbed, the one photon has to have exactly enough energy to bump the system up to the next level, or maybe up 2 levels or up 3 levels. Likewise, in order for a photon to be emitted by an atom, the amount of energy the atom is losing to go from a higher state to a lower state is the change in energy of the system, and therefore the energy of one emitted photon. And if you plug that in for energy of one photon, you can solve for the frequency of the light and or the wavelength of the light, whichever one you're looking for. Any other questions on that? All right, so try this approach on the other types of systems, the harmonic oscillator and the particle, no, this is the particle in the box, the quantum harmonic oscillator and the hydrogen-like atom. Use the formulas in the same way we use this one to try drawing a map of the different possible energy levels, and then take a look at, when you're going from one state to the next or from one state down, what are the possible changes in energy? Those changes in energy of the system have to match the energy of the one photon being absorbed or emitted. You can set that equal to hc over wavelength or h times frequency, and then solve for the frequency or wavelength of the light that will work there. So give that a try and feel free to contact me if you have any other questions, and I will see you next time. You're welcome.